Semiconductor Packaging. John D. Thomas, Alex Ruth. Book 4, Section 1, Chapter 3, Topic 1. Mechanical Fundamentals in Semiconductor Packaging. Understanding the structural basis for reliability. Introduction. Mechanical fundamentals form the cornerstone of semiconductor packaging, encompassing the principles governing structural integrity, stress distribution, and reliability of packaged devices. In semiconductor packaging, mechanical considerations are paramount due to the need to protect delicate electronic components from external stressors and ensure their operational longevity. This overview delves into the mechanical fundamentals underpinning semiconductor packaging, exploring concepts such as stress, strain, material properties, and failure mechanisms. Stress and strain are fundamental mechanical concepts crucial for understanding the behavior of materials in semiconductor packaging. A. Stress. Stress is the force applied per unit area, measured in units of pressure, e.g., pascals. In semiconductor packaging, stresses arise from thermal expansion, mechanical loading, and external forces. Types of stress include tensile, pulling apart, compressive, pushing together, and shear, sliding past each other. B. Strain. Strain is the measure of deformation in response to stress, quantifying the change in shape or size of a material relative to its original state. Strain is typically expressed as a dimensionless ratio or percentage and can be categorized as elastic, reversible, or plastic, permanent, deformation. Material properties. Material properties play a critical role in determining the mechanical behavior and reliability of semiconductor packages. A. Elasticity. Elasticity refers to the ability of a material to deform under stress and return to its original shape when the stress is removed. Young's modulus, or modulus of elasticity, quantifies a material's stiffness and is a measure of its resistance to deformation. B. Ductility. Ductility is the extent to which a material can undergo plastic deformation before fracturing. Ductile materials exhibit significant deformation before failure, while brittle materials fracture without significant plastic deformation. C. Toughness. Toughness is a measure of a material's ability to absorb energy before fracturing. Tough materials can withstand impact and deformation without catastrophic failure. D. Hardness. Hardness is the resistance of a material to indentation or scratching. Hard materials are less prone to wear and deformation under mechanical stress. E. Thermal expansion coefficient. The coefficient of thermal expansion, CTE, quantifies the change in size of a material in response to temperature changes. CTE mismatches between materials can induce mechanical stress and lead to package failure in semiconductor packaging. Failure mechanisms. Understanding failure mechanisms is essential for designing reliable semiconductor packages and preventing premature device failure. A. Fatigue. Fatigue occurs when a material undergoes repeated cyclic loading and unloading, leading to progressive damage and eventual failure, even at stress levels below the material's yield strength. Thermal cycling and mechanical vibration can induce fatigue failure in semiconductor packages, particularly at solder joints and interfaces. B. Creep. Creep is the gradual deformation of a material over time when subjected to a constant load or stress at elevated temperatures. Creep can lead to dimensional changes, warping, and mechanical instability in semiconductor packages, particularly in high-temperature environments. C. Fracture. Fracture occurs when a material fails catastrophically under excessive stress, resulting in the separation of material into two or more pieces. Fracture can occur by brittle fracture, where the material fails without significant plastic deformation, or ductile fracture, where the material undergoes plastic deformation before failure. D. Delamination. Delamination refers to the separation of layers or interfaces within a semiconductor package, typically caused by thermal cycling, moisture ingress, or adhesive failure. Delamination weakens package integrity, compromises thermal dissipation, and increases the risk of device failure. Thanks for watching. Please like, share, and subscribe.